Hello, everyone. Today we are going to do a quick but very substantial review of a ton of reactions. Basically, mostly reactions introduced in this most recent unit, plus a few throwbacks to the previous unit. I'm going to have a lot of information on the screen at all times. Um, Part of this is just so that you can kind of see where we're going, and part of it is so that I don't have to uh, spend most of the video writing things down. So let's just quickly have a look. Like I said, we won't be going into depth. We won't be doing examples, but we're just going to look through all the different reactions that you could see when we're dealing with alkenes and alkynes. Okay, so alkynes primarily react through addition reactions, and all of these initial ones are electrophilic addition. Okay, so electrophilic addition involves similar mechanisms. Um, I say all of them are electrophilic addition. There are a few exceptions, but they all involve addition, we'll say. So the first is we can add a hydrogen halide like HCl, HBr, or well, just those two add easily. Those follow Markovnikov arrangement, and they allow for rearrangement due to the presence of a carbocation intermediate. Okay, so these are going to add Cl or Br onto the most substituted carbon near the double bond, and they do allow for rearrangement. Okay, this one, HBr and peroxide, this is unique to HBr. It follows a free radical mechanism that we didn't learn, but it adds that Br on the anti-Markovnikov spot. So it could be useful for making a primary haloalkane. I've got three different mechanisms for adding hydrogen to either add to an alkene to make it an alkane. That would be using metal such as platinum, nickel, or palladium, or add it onto an alkyne to make an alkene. That could be done with P2 or Lindlers. These are considered poisoned catalysts because they contain metal plus something else. These would allow for syn addition of the hydrogen to make a cis alkene. Or we could use sodium metal or lithium metal with ammonia. Okay, and in your textbook, you might see it written something different, like I think it's like ET2NH with ammonia, something like that. The main thing is this allows for trans alkenes to be formed. Okay. Next, we've got hydration reactions. We did a video on that earlier. 3 different types of hydration reactions. The first, most common one is acid catalyzed. This is most likely what you will do if you do a lab in college. It's safe. It turns an alkene into an alcohol. It follows Markovnikov, and it allows for rearrangement. So this would not be super useful for making a primary alcohol unless you were using ethene. Oxymercuration demercuration, similar Markovnikov addition of hydroxide group, but it does not allow for rearrangement. So this would be more useful if you knew that you had a methyl branch somewhere and you didn't want rearrangement to occur. The main reason this isn't done in college labs is due to that mercury, and one of the products of this reaction actually is mercury, which is not easy to dispose of, and typically we don't expose students to it. Hydroboration, I said some of these are not really electrophilic addition. This one, a little bit different. The boron actually gets added in place of where hydrogen gets added in these other ones. This allows for anti-Markovnikov and also gives you those intermediates where boron is actually bonded to a bunch of R groups, which eventually become alcohols. Boron adds to the anti-Markovnikov spot, and that's eventually replaced by that hydroxy group. Okay, halogens, that's Cl2, Br2, those can be added either in a non-aqueous solvent like CCl4, and this gives us a dihaloalkane like 1,2-dibromo something. It's anti positions. Okay, so the 2-bromine or 2-chlorine would be anti to each other if those are chiral centers. If it's done in an aqueous environment, we get a halohydrin. This is just so much more likely to happen than getting 2 halogens added on, because water is just going, in an aqueous environment, water would be much more present than say Cl- or Br-. Okay, also anti-position. Okay, and lastly, concentrated H2SO4 can be added. We didn't actually talk much about this one, but that's going to add a hydrogen onto the double bond and an S or an HSO4 group onto the double bond. All right. So I'll just draw it for you. Okay, it's going to look something like this, called a sulfonate. That is not very stable, and once water is added, the sulfonate gets replaced with an OH to make an alcohol. Also, electrophilic addition. Okay. The other types of reactions we learned were oxidation reactions, where we learned a few of them. Hot KMnO4 is used to cleave double bonds. Depending on the location of the double bond, primary carbons become, depending on where they're at, primary carbons will become CO2 if they're right on the end. Secondary carbons will become COOH, carboxylic acids, and tertiary carbons become ketones. So this is mostly used as a method for sort of figuring out where the double bond is by looking at the products. Okay, if we use cold dilute KMnO4, this reaction happens to a lesser degree of oxidation, and rather than getting CO double bonds forming, we just make 1,2 diols in place of the double bond. OSO4, osmium tetroxide, also produces those 1,2 diols. It's preferred over the cold dilute KMnO4 due to the fact that a side reaction of KMnO4 is what we just mentioned before. That's cleaving the double bond and oxidizing it beyond where you want it to go. O3 is similar, but it's sort of in between these two. It will oxidize tertiary carbons to a ketone, but secondary and primary double bonded carbons get oxidized to aldehydes instead. Okay, this is also done by hot KMnO4. It makes an aldehyde, but then it further oxidizes that aldehyde, so the aldehyde is very short-lived. If you had an aldehyde in your molecule somewhere, KMnO4 would also oxidize that, although we didn't talk about that in detail, but that's something to look out for. Alkynes. Alkynes can do most of the reactions that alkenes can do, with a couple ones that are unique to it. It can react with NaNH2 in 2 different reactions. One is to form that carbon anion that can be used to undergo nucleophilic substitution and extend the carbon chain. But we can also use this reaction to make alkynes if we have a dihalide. Okay, so whether it's a vicinal dihalide, such as this 1,2-dibromo, or a geminal dihalide, like 1,1-dibromo, whatever, both of those could have these bromines eliminated using NaNH2 to form an alkyne. Okay, and it's important that we have 2 of them on adjacent or the same carbon to form the alkyne. If we only had 1, we would only make an alkene. HX, that would be HCl, HBr, or X2, which is Cl2 or Br2, can both be added to alkynes, but unlike how they react with alkenes, we can choose to react either 1 or 2 molar equivalents. If we reacted only 1 molar equivalent, then we would just take that triple bond down to a double bond. And suppose we were adding HBr, we would be left with an alkene with a bromine on it, something like a bromoalkene. Okay, if we reacted a second molar equivalent, we could take that to a geminal dibromo substance. Okay, and lastly, E1, E2, SN1, SN2. These are reactions that we've learned in the past. You just want to keep them in mind. All of the dehydration reactions we learned are E1 reactions. Okay, so that would be taking our alcohols, bringing them back to alkenes. So anytime we have E1 or SN1 reactions, we form a carbocation as an intermediate, which allows for rearrangement. There are 3 types of rearrangement that can occur. The new one we learned is ring expansion. That takes priority over the others, followed by hydride shift, followed by alkyl shift. To note, ring expansion occurs with rings that have fewer than 6 members and are adjacent to a carbocation. Okay, so the carbocation is not part of the ring, but it's adjacent to the ring. Something like this would result in a new carbocation forming, in which the carbocation is now part of the ring, and the ring is expanded to be a 6-membered ring. Okay. Just remember SN2, E2, they're always in competition with each other. For this chapter, that wasn't so much of a factor, but a couple of things to remember, like heat favors E2, or favors elimination over substitution, and bulky nucleophiles favor elimination over substitution. I'd say those are probably the 2 most common factors. Right? So that is all I wanted to review. It is a lot of stuff. I would recommend writing this down, keeping your notes organized so that you have quick access to them. All right. Thank you all. Good luck. If you have any questions, please email me or send me a message on Google Classroom. Have a good night.